Hi and welcome back to a new video. Today we want to experiment and investigate a myth that has been around as long as I can remember in the PC industry. At some point, if you're building a new PC, you will come to the decision of how to place the direction of your fans. Do you want to have cold air intake on top, or do you want to push out hot air outside of your case? And especially on German forums, I often read, hey, support the chimney effect, most likely known as stack effect in the English community, and just push out the hot air from inside. But what about this? Is there even a stack effect or chimney effect? Is your PC a chimney? And does that even work? That's what we want to find out in today's video. Thermal Grizzly Duronaut is our new high-end thermal paste and the successor of Cryonaut. It's even better performing, it is much easier to apply, it is cheaper, and it's much more durable. That's where the name comes from. Especially if you're now maybe considering to buy a new PC, then I would highly recommend that you're looking into this thermal paste. So let's continue with this video. Most of the time, these type of recommendations to support the stack effect come from the common knowledge that hot air rises. As an example, we are looking at this system that we built a while ago on my channel. It's custom water cooled, but that doesn't matter for the moment. We have a big radiator that's placed on top. You see the black tubing going there, and the black tubing is directing the hot water into the radiator. That would be exactly the same if you would use just a normal conventional AIO. And underneath you can see the three fans that are using basically the warm air inside the system and pushing it through the radiator, cooling down the water that is sitting in the radiator, and then just hot air coming out of the system on the top. Most people are absolutely aware that hot air rises, but that's not stack effect. Hot air rising is caused by the molecules just having more movement if they're warmer, and that's causing a different density, which causes the hot air to rise. But that's natural convection, that's not stack effect. In contrast to natural convection around an individual heat source, the stack effect describes a large-scale airflow through a vertical enclosure or channel or chimney. Warm air inside the enclosure has a lower density than the cooler surrounding air, and therefore creates a small pressure difference between the lower and upper openings. This pressure difference then causes colder air to enter at the bottom, while warm air leaves at the top. The effect becomes stronger if you increase the height or the temperature difference. This means that natural convection is indeed the base for the stack effect, but you need an enclosure. You need something big, like a big case or like a big chimney, to create this pressure difference inside. Otherwise, you would not have the flow inside. If we go back to our example, this PC build, we can assume that our case is basically the enclosure, the chimney. It has a height of 55 centimeters, and we can assume an ambient temperature of 20 degrees Celsius. Maybe assume internal temperature of 40 degrees Celsius. This would leave us with a stack effect and a pressure difference of 0.4 Pascal. Pascal as a unit is usually not that easy to imagine, especially when we're talking about very little pressure like 0.4 Pascal. So that's why we have an example of the water column. So you just imagine you have this hard tube, it's 1 meter long, and you fill it with water, like 1 meter of water. Then you would have a pressure of 0.1 bar on your finger on the bottom. To get the pressure of 0.4 Pascal, you would have to fill this hard tube with 0.04 millimeters of water. Basically, not even the size of a human hair height of water, and that's the pressure you would feel on your finger. You would not be able to feel it. It's basically not existent pressure, the 0.4 Pascal. But what if we just take a radiator and then just build our own enclosure, chimney basically, to create a stack effect and see if it does anything or not? I have no clue. For this, we first have to build a custom water-cooled system. I'm using an AMD CPU, and I also want to throttle down the power consumption, so we have a controlled heat output inside our radiator. Super simple assembly. We just have the CPU block that's being fed by the pump, and then we will also loop in the passively cooled radiator, connecting all of this with soft tubes. By the way, we also have our own soft tubes now, so 16 millimeter and also 13 millimeter, and I just think they perfectly match with those matte nickel fittings. Using this radiator prototype from us, it's the HC240, so 240 millimeter radiator, and I will place some standoffs in the aluminum shell to just elevate this up a little bit. Everything is set up and running, so very simple custom water cooling loop. Added the radiator in. You can see there's also yeah, good spacing underneath so the air can just freely intake from the bottom. I also added this thermometer on the side, which is taking the temperature from this fitting. So that's the water temperature going to be, and that's already increasing. As you can see, it's already 31 degrees Celsius. That is because I'm already running the system under load. I configured PBO so that the CPU is constantly pulling 100 watts. So we have a constant heat input into the system. But first I have to even find out if 100 watts passively is working with such a radiator or not. So the general approach will be that I first have to find steady state in the system. First have to figure out if this is capable of dissipating 100 watts or not. Then we take the water temperature and then we will stack up these things, which are basically huge fan shrouds. A single one of them is 20 centimeters. They're 3D printed out of PLA. I have 6 of these. 20 centimeters each. I also have a single 10 centimeters, so in theory we could stack up 1 meter 30 on top of the radiator and thus probably enhance the stack effect if it's even there, and that would then lead to better temperatures. That's the theory. We will find out. Making use of the time until the system finds its steady state, already added 4 of those elements together, so that makes 80 centimeters of an enclosure. I'm then just fixing them together with M4 screws, which maybe sounds a bit over the top, but I just want to make sure they're really tight on each other with no gaps in between. It's been 1 hour and 20 minutes. Temperature does not really change anymore. It's about 61.5 degrees Celsius. Now I have this fog machine that I want to use. Put it underneath the radiator and see if this helps to visualize the natural convection, if there is any. Of course, I can feel it if I just put my hand above it. I can feel that hot air is rising, but that doesn't help you in the video. That's why I want to try this. Of course, you can see the fog rising. Well, above you can see it a bit better. So here, definitely pushing up, like this. But it's hardly pulling it through. This means we will go ahead stacking those elements. You could see the temperature is changing a little bit. So in the past 10 minutes, 0.2 degrees Celsius. That is not much, so we can go ahead doing this. We'll start with the 10 centimeter one and then see how it goes. This is super interesting. The 10 centimeter one alone seems to be helping. You can see this is slightly decreasing. At least it went down from 61.5 to what we're seeing now. Just going over back to the system again, you can see nothing changed. It's still pulling 100 watts. CPU is really warm, but still outputting the same 100 watts. And the 10 centimeters alone seem to be already helping. Let's see if the fog machine brings out something already, but yeah. It's not really conclusive with a fog at this moment. I honestly did not expect this to do anything, especially with only 10 centimeters, but it already helped to bring it down to 61. So we will stack another 20 centimeters on top and see what this changes. You can see the temperature still keeps going down. I'm still working on the second extender. But this is also far more than I expected, far more than measurement tolerance, because the room temperature is still at 21.5 degrees Celsius, did not change, but we already see a change here of far more than 2 degrees Celsius. So that is more than I expected, especially for the small thing that we added on top. Now, of course, the question again, if the fog machine tells us anything, and I actually think so. So if we just do this, you can see, I would say, a difference in speed of the fog that's surrounding the chimney and the stuff that goes up inside. Yeah, there's definitely a difference. Small difference, but there's a difference. I waited another half an hour and it doesn't really change anymore, but we gained 6 degrees Celsius just by putting these two on top. And now we will stack the big one. Okay. Almost goes up to the ceiling, so that's a pretty long one, but it has a huge effect. I didn't even have the time yet to bolt it together, but you can see how it brings down the temperature. It hasn't even been 5 minutes and it's already down by 5 degrees Celsius. That is much quicker, much more than I expected. So I'm trying to use the fog machine now and then see what it changes. I can clearly see how it sucks the air in. So that is a lot different to before. Can definitely see how it works. Just have to make sure that I'm not setting off the fire alarm. The big tower also definitely helped to bring down the CPU temperatures. We were at a peak of over 90 degrees Celsius and we're now at about 72. You can still see it's the same package power draw. That's an interesting camera setting, I assume. I had to zoom all the way out to get this thing onto the shot. And we have the final temperature results, almost another 30 minutes, and we have almost 19 degrees Celsius lower temperatures. That is crazy. That is more than I anticipated, more than I expected. And this, demonstrates the stack effect, or also known as a chimney effect. We built a chimney. That's what we have here. That is not the same what you have inside a PC case. In PC case, you have just the natural convection. You have hot air rising, but you would not have exactly this. You might have the effect of the first 10 centimeters, but inside a PC case, there's just too many other variables, like, fans blowing from different directions, and then you might have like an air-cooled graphics card that would definitely just completely ruin whatever it could build up. What you definitely have is the natural convection of the hot air rising. You can support this by putting your fans in the appropriate direction if you want to, but that would be the real stack effect that you probably don't have inside a case. I mean, this would be an odd case. But I think there was an interesting experiment. I did not expect that you can gain almost 20 degrees by just stacking those 3D printed things. I hope you enjoyed this video. See you next time. Bye bye.